Similar to Fourier's law, which is the constitutive relationship between the flux due to conduction and the local temperature gradient, Newton's law of cooling is the constitutive relationship for heat transport from a solid system where conduction is the mode of heat transport inside and there is a convection outside the solid. Okay. So the way to describe is, supposing if we have a solid here, okay, and there is some fluid which is flowing past this solid, okay, so this is x equal to 0, could be flowing at a certain velocity v, okay. We will see a lot more about it when we discuss convection topic, maybe about 10 lectures, 10, 15 lectures from now, okay. And so there could be a transport coefficient h, okay. So we have to now define a heat transport coefficient and the reason for defining such a coefficient is that, note that here is heat transport across different phases. So here this is a solid and this is a liquid. So you have transport across different phases and so we need to define some sort of a coefficient. That's a fictitious coefficient and we will actually see how to estimate these coefficients, okay. It's for convenience purposes such a coefficient has been described, and so Newton's law of cooling simply says that Q prime at x equal to 0, that's the flux at x equal to 0, should be equal to the heat transport coefficient h, and supposing I assume that the temperature here is T infinity, and if the temperature inside, so if this temperature is higher than the temperature at the boundary, okay, so this is the surface temperature. So if I assume that the fluid temperature is higher than that of the solid temperature, which means that the heat is transported from the fluid to the solid, then one could define the flux as T infinity minus Ts, which is basically at x equal to 0. So that's the Newton's law of cooling, and so if I plug this into my third boundary condition, I'll get minus k dt by dx at x equal to 0 equal to heat transfer coefficient into T infinity minus Ts, or you can say T at x equal to 0. Okay. This gradient will take care of that. So note that when T infinity is less than Ts, then you're going to have a profile which is different, okay. Supposing if T infinity is greater than Ts, you're going to have a profile which looks like this, right, because there is heat that is going from the fluid into the solid. Now supposing if T infinity is less than Ts, you're going to have a different profile. So the gradient will take care of the sign whether it is T infinity is greater or less than Ts. So this is a general form irrespective of what is the sign of T infinity minus Ts, because the gradient is what is going to dictate what is going to be the sign. And so also you should note, it's very important to note here that this gradient describes the flux inside the solid, and this formula here represents the flux just outside the solid. So this is a balance between flux of the heat transport just inside the solid and flux of heat transport just outside the solid. So this balance really comes about because we assume that the temperature is continuous. It's a continuous variable. Because it's a continuous variable, there has to be a gradual change in the temperature, and if the way to account it mathematically is that the gradients have to be equal. That's how you ensure that the temperature is a continuous variable, that is, it changes continuously without any jump at the boundary point. Okay. So this is very important to understand how this balance comes about. You will see very often, not just in this course, in several other courses in reaction engineering, etc., in the future, you will see that these kinds of flux balances at the boundary will come into picture. Okay. So let us take a specific example. So let's say we start with a a one dimensional steady state conduction process. Okay. So we start with a simple one dimensional conduction. So let us say we have a slab. So that is a slab, and we assume that it is one dimensional. So let us say that the conduction process is in the x direction, okay. And if we assume that so this is the temperature axis. So if the temperature here is T2, and let us say temperature here is T1 and T2, okay. So at x equal to 0, the temperature is T1, and x equal to L, the temperature is T2. Okay. So what is the energy balance for this? So keep in mind that the general energy balance, so you should always try to sort of look at the general framework. It's del square T plus Q dot by K equal to rho Cp by K into dT by dt. Okay. So you can always start with the general energy balance. So we said that it's a steady state system, so the time derivative goes to 0. So dT by dt is 0 because it's a steady state system. We are considering a steady state problem, and then we said it is one dimensional system. So which means that the Laplacian is simply in the x direction, d square t by dx square. Okay. And supposing if we also assume that q dot is 0, that is there is no energy generation or loss inside the system, no matter whatsoever, and so q dot is also equal to 0. So these are the immediate translation of some of the assumptions that we have made, and so based on this we can write a simple model. Will be k into d square t by dx square equal to 0. That is the simple model equation for the system that we have considered, where it is a 1D steady state conduction with no heat generation / heat loss. What are the boundary conditions? So at x equal to 0 equal to T1 and T at x equal to L equal to T2. Okay. Can I solve this equation? Of course yes, you have done this. It is not a big deal. So temperature is given by T2 minus T1, T2 minus T into x by L plus T1. Okay. So that is the temperature distance. Oops, T1, T2 minus T1 into x by L plus T1. So that is the solution. Very trivial. If you didn't understand how this comes about, you should go home and try to work it out and get this solution. Very easy to get this. Okay. Alright. So now we want to find out what is the heat transfer rate. Okay. We want to find out what is the rate at which heat is being transferred for this system. So remember, in the last lecture I mentioned that heat transfer rate is the quantifying description of the transport of heat via conduction, and in general it is the quantifying description for any heat transport process. So you need to find out what is the heat transfer rate, and also you should keep in mind that it is very important from application point of view. So when you are looking at a certain system, what somebody wants to know is how much heat is being transported, what is the amount of heat that the system would generate at one wall or one end, and what is the amount of heat that I am supposed to take from that end of the wall. So this is an important question you will always have when you, from the application point of view, but finding the energy distribution is really leading towards finding the heat transfer rate, and the way to find out is very simple. We know that minus K, area of heat transport, multiplied by the corresponding gradient. So it's very easy. What is the gradient? dt by dx? It's T2 minus T1 by L, right? So it will be minus K A into T2 minus T1 by L. Okay. So with this framework, we could introduce what is called the resistance that is offered by the system. So we should reflect back one of the points that we discussed a short while ago. What is meant by thermal diffusion? We said there are two competing processes which are occurring. One is the ability of the system to store heat, and the other one is the ability of the system to transport heat because of conduction. So one way to look at is the resistance that is offered. A clean and elegant way to capture the one of the competing processes is to calculate the resistance that is offered by that particular system for that process. It's similar to what you would have seen in your electrical engineering or some of the electricity things you have studied pre-JEE. Okay. So you can find out what is the resistance offered towards conduction. And the way it is defined is, so R is generally is the symbol I will use for resistance. So R for conduction, sometimes I use a subscript, sometimes I don't, but generally R means the resistance which is involved. Okay. So resistance offered is simply given by delta T divided by the rate at which heat is transported in that direction. Okay. And that is given by T1 minus T2 divided by K into A divided by L. Okay. So I have just taken the minus sign inside, and so that is nothing but L by K into A. So the resistance that is offered by the system for thermal diffusion is given by L by Ka. So note that it is not just conductivity, but also the length and the area of heat transport plays an important role here, and that you would sort of intuitively guess. If the length is longer, then you have a longer span for diffusion to occur. If the length is smaller, you have a shorter span. So obviously you would intuit that length and the cross sectional area is going to play a role, and that sort of clearly comes out from the analysis of the model that we have written so far. Okay. So therefore we can easily translate this into a simple resistance network . So we can easily translate it into a resistance network, and this sort of network you are familiar with from your pre-JEE days, where we can say that there is a network and it is connected by the temperature of the two surfaces of your system, and the resistance of the network is given by L by Ka. Okay. Alright, so we can now add a small complication to it, or rather small addition to it. So let us say that there is some fluid which is flowing on both sides. Let us say I call this the hot fluid, okay, and I call this the cold fluid. Okay. And if the temperature of the hot fluid is T infinity 1 and temperature of the cold fluid is T infinity 2, okay, what will be the resistance offered for heat transport from the hot fluid to the surface? How do we find that? We need to find the resistance which is offered for heat transport from the hot fluid to the, let us say, surface at x equal to 0. How do we find that? It is described by Newton's law of cooling. Okay. So Q, which is the rate of heat transport at this location, is given by H into A, which is the heat transport coefficient, multiplied by the cross sectional area which is outside the board, into T infinity comma 1 minus T at x equal to 0, which is T1, right. So that is the rate at which the heat is being transported from the hot fluid to the slab, and we can use the resistance network concept, and we can say this is the convection resistance, and that is simply given by 1 by HA. It is very simple to see this. This is nothing but T infinity comma 1 minus T1 divided by Q. Very easy to see this. It's the same formula I have used, delta T divided by Q. Okay. H depends on many things like flow velocity, properties of the fluid. We will see all that. We will see how to find H. It's not very easy to explain in the next 5 minutes. So there are about almost like 12 lectures we are going to have in this course, which describes what is the method by which you can estimate H. So it really requires that much time. So we will actually look at it sometime around the mid-sem and after that. Okay. All right. So now therefore we can now extend this resistance network into 3 resistances. Okay. So supposing if the heat transport coefficient from the hot fluid to the slab is, let's say, H1, and from the slab to the cold fluid, if that is H2, okay, if that's the heat transport coefficient, then we can say that the temperature of the hot fluid is T infinity 1 and the resistance offered for heat transport is 1 by H1A, okay, and the temperature at the boundary is T1 and the resistance offered by the slab for heat transport inside the slab is given by L by Ka, and the temperature on the boundary is T2. And similarly, the resistance here is given by H2 into A. So you can almost read out what the resistances are. So that's the power of the resistance method that you've learnt in your electricity things. So you can almost read out the properties and present it in terms of the network. And there is something even more cute you can do. So if this is the total amount of rate at which the heat is transferred from the overall system from the hot fluid to the cold fluid, then one could represent Qx as the total resistance, or maybe we should rewrite it. So one could say that the overall resistance is simply given by the overall temperature difference divided by the total amount of heat that is being transferred, right? It's very easy. What is the overall resistance? It's in series, so just sum of the resistances, very trivial. Okay, so it's 1 by H1A plus L by Ka plus 1 by H2 into A, right? So that's the overall resistance that is offered by the whole system together. So this gives you an elegant opportunity. So if you know what are the measurable quantities, so this is the first time I am using measurable quantity. So when you are doing any modeling work, when you are representing any system using mathematical representation or model equations, you must always understand what are the observable quantities. What is it that you can measure experimentally? What is it that you can measure in physical system, in actual system? So whenever you have, if you take the example of the geyser, so all that you can measure is the temperature of the fluid that comes in and goes out. So can we write our model equations and can we write our mathematical expressions in such a way that we are able to use the observable parameters or observable quantities in order to estimate the properties of the system. For example, it could be, I want to know what is the temperature T2, but all I know is I can only measure the temperatures of the outside fluid. So can I use the resistance network? So that's what these kind of resistance network method provides you an elegant opportunity to use the measurable quantities and find some of the quantities that is not known to you via normal experimental measurement. Okay. So we are going to see some examples of these mostly in the next lecture. So we'll just take a little bit more complicated case of this resistance network and we'll finish with that for today's lecture. So let us take the next example of composite wall. Composite wall. So supposing instead of one wall, I have multiple walls which are stacked next to each other. And this is a very, very common thing that you would observe in an insulating system. So supposing if you have an insulator, usually it is stacked with different walls and each of them have different conductivities. It's very often very common to design system with multiple walls which actually have different properties. Okay. So you can have K1, K2 and K3, each of these could have different conductivities. So you could imagine that you might want a certain material which is exposed to the hot fluid, but you don't want the second material which has better conductivity to be exposed to the hot fluid, because there could be some reactivity with the fluid. So in order to avoid that, it's a very common practice to design these kinds of composite walls. And so if I assume that the length of this first wall is L1, length of the second wall is L2, length of the third wall is L3, and if I have, let's say, hot fluid which is flowing before the first wall and there is a cold fluid which is flowing after the third wall, and if the temperature of the hot fluid is T infinity 1, and if the heat transport coefficient for Newton's law of cooling is H1 here, and if it is T infinity 2 and H2, and I can now specify temperatures T1, T2, T3 and T4. So I can easily read out and draw the resistance network with really minimal effort. So how many resistances are there? How many? 5, right? So we have 5 resistances. The first one being the resistance offered for transport of energy from the hot fluid to the first slab. So that is 1 by H1 into A, comma 1, T1, T2, and this is L1 by K1A, T3, L2 by K2A, T4, L3 by K3A, and this is T infinity comma 2. And that's the total amount of heat that is being transported from the system from hot fluid to the cold fluid, and that's Qx. Okay. So I think it's a good point to stop. So in the next lecture, what we are going to see is, we said we assume that the cross sectional area is constant. So we are going to start with a specific case where the varying cross sectional area system, and we are going to see how the equations are going to change and how the temperature distribution is going to change. By the way, one important point before we close, what will be the temperature distribution in this slab? It's linear, so very obvious from the expression. So it's linear temperature profile. And what will be the temperature profile if there is a varying cross sectional area, and we look at other geometries? We looked only at Cartesian coordinates here. We'll start looking at radial systems and other coordinates. Okay.